In this video we're going to look at how to analyse an op-amp circuit. So we're going to use the golden rules, which there are two of them, along with Kirchhoff's current law and Ohm's law, and these three little basic constituent laws are going to allow us to analyse all the op-amp circuits that we're going to be using in this course. So the golden rules, we've seen these before, but we had never termed the golden rules. So these are that no current is going to flow into the inputs, that's the V minus or V plus, so no current into the inputs. And also with negative feedback, the voltages at V plus and V minus are going to be equal. So with these two simple rules and also Kirchhoff's current law, we can analyse all the circuits we're going to be looking at in this course. So Kirchhoff's current law really just says that if you sum up all of the currents into a node, they will equal all of the currents out of a node. So in this instance here, the node is here, so we can call that node A. So I1 plus I2 is equal to the current flowing out of the node, which is I1 plus I2 there. Okay, and Ohm's law can be written R equals V upon I, or if you transpose it, we get V equals IR, or transpose it to as I equals V upon R. So we will be using this one here throughout our the rest of the course. Now the thing about analysing this is to be consistent, and you'll see what I mean when I move on to the next page. So we will be looking at an op-amp circuit at the very end, but let's start off with a simple little node here. So you've got a simple little circuit. So you've got an input voltage here, V in, output voltage V out. You've got three resistors, R1, R2 and R3. R3 is sitting at ground, and we've got the centre voltage there equaling VA. Now the simple way to do this and ensure that you get it right every time is that whenever you look at the currents into this node, in order to get the currents you use I equals V upon R. So the voltage is going to equal the volt drop across these resistors. So if we say V in minus VA, then we draw the current in this direction. So you draw the current from V in to VA. So the current gets drawn as an arrow in that direction. So we are defining the current as flowing in that direction. So that current there plus the current that flows in this direction here, so this is a yellow arrow here, that will be our V out minus VA. So that's the current from V out to VA flows in that direction there, from V out to VA. So that's that yellow one there. So that current plus that current, according to Kirchhoff's current laws, must equal the current flowing out of this branch. So the current flowing out of this branch here, we could define that current as in this direction here, down the way, which would be our VA minus, well that's just a ground, so which is 0 divided by R3. So you could say that the sum of these currents is the current here in this branch are along R1 plus the current in the branch here along through R2 is equal to the current down in this direction through R3. Now, to talk about being consistent is we could equally have defined it with the currents flowing in different directions. So we could have defined it the current is flowing up through R3 and out through in the direction of R1 and the direction of R2. In which case we would be saying then that the current here, the blue one, is going to equal VA minus V0. So the current from VA to V0 is in that direction. That's that one there, divided by R2 plus the current from VA to Vin. So that's VA minus Vin is the current in that direction, all upon R1. Well, that's going to equal the current that has flowed into the branch from R3. In that case it would be the 0 minus the VA upon R3, would give us the current in that direction. Okay, so we end up with that one there. Now, if we were to multiply these out, so we just say Vn upon R1 minus Va upon R1, and you multiply this one out, and we also take the Va upon R3 across, so you end up with a minus Va upon R3, and we'll do the same at the other side. Then you'll notice that the equations actually are the same. The only difference is the direction in which the current is defined. So I could multiply this side here by a negative, and this equation here would become exactly like that equation there. Or equally, I could multiply this equation here with a negative and it would become that equation. The only difference between these two are how we've defined the direction of the current. So the only thing you need to take out of this really, in order to design these circuits or analyse these circuits, is to ensure that whenever you define the volt drop across a resistor, if you say the voltage from V in here to VA will give you the current in that direction from V in to VA. So that's the only thing you have to remember there. So let's use that, and we'll have a quick look at our first op-amp circuit. The first op-amp circuit we're going to look at here is an inverting amplifier. Now we will go back to this in a future video and we'll look at it in multisim, and we'll go in and we'll see it actually working. Okay, this is just I've done it in this video here just to show you how to analyse it. So we have our op-amp here. The positive side is connected to ground. We've got an output voltage here, we've got an input voltage, we've got a resistor R, we've got a feedback resistor RF, so you can see the negative feedback there into the negative terminal. So we know from our golden rules that the V plus is going to equal V minus, okay, but the V plus is equal to ground. Okay, so in this case here, V plus must equal V minus must equal 0, so that's our first golden rule. And then we can start analysing this, so we can look at the current, say in the blue arrow here, so the current in this direction here, so that's going to be our V out minus, well that point there is our V minus upon our value RF, okay, so that's V out minus V minus upon RF, which is this one. And then we're looking at the current, and if we define the current in this direction here, so then the blue arrow there will give you current from V in minus V minus upon R. When we add both those currents together, well, we know that there's no current flowing in to this input terminal, so both these currents are coming in the same direction and they can't flow out of here, so both these currents must be equal. Okay, so if we add them up, equal, but they'll be equal, but they're defined in opposite directions, so when we add them up they're going to be equal to 0. Okay, so what we need to do now is just move this equation round about and transpose it and try and find out what VO is. Okay, so we just simply have V in upon R, and we know that V minus from our golden rule is equal to our V plus, which is equal to 0. So we'll have V in upon R equals, and at this side here we'll take this across to the other side, will be minus V out upon RF. So then we can write that in as V out is equal to minus RF upon R times V in. Okay, so that there is the final equation there which we were looking at. So it's telling us that the output voltage is equal to the input voltage times the ratio of the resistor RF to R, and it's also going to be inverted because there's a negative sign there. Okay, so that there is our inverting amplifier, and again we'll see that again whenever we have a look at it in the videos to come. Okay, so thank you for listening, and I'll get you next video. Goodbye.